Всім доброго дня. Так, мене наче чути. Зараз ще декілька хвилин почекаємо і починатимемо. Так, чи будете ви якби шерити лекцію вашу, чи. Так, я потім скину після лекції, звичайно. Звичайно. Ні, ну можете фотографувати для конспектування. Що це. Добре, давайте, мабуть, будемо починати, тому що там після мене якраз буде Айзек, він ремоут, і щоб його теж не зсовувати дуже по графіку, якраз зараз 15:03. Отже, доброго дня всім. Мене звати Володимир Безгуба. Я працюю в Київському академічному університеті як фізик, фізик-експериментатор, а також за сумісництвом я працюю завідуючи лабораторією машинного навчання КАУ. І вона така міждисциплінарна, але в тому числі мій напрямок досліджень там теж представлений, котрий є, як бачите, Condensed Matter. Точніше, це Condensed Matter — це насправді така дуже широка тема. Я коли її подавав, я спеціально взяв її максимально широку, щоб все, якщо що, охопити. В основному буде, звісно, про solid state, про надпровідність, про експериментальні методи, про методи розрахунків, про електронну структуру. Зараз дещо більше розкажу. Також ще цікавий нюанс, до речі, там от є емблемка QMATS. Зараз. Як? Ну, добре. QMATS — це проект Core of Excellence. Ми виграли його в КАО під керівництвом Олександра Анатолійовича Кордюка. Таких проєктів на всю Україну 4. Якщо ви були на першому дні відкриття школи, розповідали якраз пані із компанії Ензим, вона якраз розповідала про те, що вони також виграли один з цих проєктів. Тобто це така крута штука, яка дозволить розбудовувати лабораторії саме по фізиці твердого тіла у нас в Україні в КАУ. І я пізніше ще згадаю про це, коли буду більше про експеримент розповідати. Отже, коротко окреслю, що я планую вам взагалі розповісти сьогодні та завтра. Це все на 2 дні, не на один. Короткий вступ взагалі в квантову фізику, тому що я розумію, що аудиторія різна, і хтось забув, хтось взагалі з іншої галузі. І я просто коротко пройдусь по якимось основам, потім поясню, чому є запит до машинного навчання. Як можна, чи можна порахувати це все, чи потрібен експеримент, чи можливо достатньо взагалі, просто порахував матеріал, зробив круту батарею, яка може тримати весь день і важити 1 кілограм, і нічого більше не треба. Потім розкажу дещо про прогнозування матеріалів і пошук нових матеріалів. А по експериментальній частині я подивлюсь, на чому я зупинюсь, але, скоріш за все, на завтра буде повністю експериментальна частина. Отже, почнемо трошки з фізики. Тобто, що взагалі таке тверде тіло? За визначенням, тобто кристал — це є типовий приклад типу твердого тіла. І за визначенням в ньому є трансляційна симетрія, тобто у вас є якась елементарна комірка, яка постійно повторюється, і от вгорі зображено три різні кубічні градки. Проста ГЦК грана центрована і центрована кубічна. І ну, в даному випадку ніби все просто. Тобто ми просто беремо, ми знаємо, що кут між ребрами 90 градусів. Кристал складається в ідеалі з безкінечного такого повторення ячейок. В реальному житті зрозуміло, що є якісь кінцеві розміри у кристала. І на перший погляд, ніби все просто, але таких кристалічних граток може бути дуже багато. Решітки, ну, їх можна пограбувати в решітки браве. Вони розбиваються на багато груп симетрії, і крім того, треба враховувати, що ці вузли вони не є всі однакові. Тобто, якщо, наприклад, дивитися, ну, простий приклад, натрій хлор ось тут зображений. Якщо взяти елементарну комірку, то тут будуть, очевидно, різні атоми натрію і хлору, які якось взаємодіють між собою, там є ковалентні зв'язки, трошки іонні. Тобто, і це все взаємодія відбувається, по суті, за рахунок в основному електронів, про що трошки пізніше скажу. І от як показник того, що це такий дуже простий випадок, коли вона у нас просто кубічна решітка. А ось справа, наприклад, залізні надпровідники, їх відкрили вперше в 2007 році. Випадково це високотемпературні надпровідники, тобто ті, які не описуються теорією БКШ, яка класно все описувала, передбачала, а потім в якийсь момент виявилося, що ні. Виявляється, вона не може все передбачити. І на сьогоднішній день це одна з невирішених задач фізики, як створити кімнатний надпровідник, тобто надпровідник, який буде мати надпровідність при кімнатній температурі, і чи взагалі це можливо. Тобто принципово ніби нічого не забороняє, але як це зробити, теорії розуміння якогось немає. Є тільки емпіричні теорії, які можуть передбачити щось, що вже зробили, а не нове. І як бачите, тут ну, складні шароваті структури, просто як приклад. От, це те, що я казав, що різні решітки, різні градки брава. Тобто, очевидно, що постійні градки можуть відрізнятися. Це ну, вони не обов'язково всі будуть А одного розміру, плюс можуть бути різні кути між ними, ну, триклінна симетрія, гексагональна, тощо, тощо. Ну, а це просто приклад кристалу, який ми міряли на синхротроні. Ось, за рахунок чого взагалі, до чого тут електрони, електронна структура, у всіх цих атомів, які входять як елементарні будівельні блоки в склад кристалу, навколо них крутяться електрони. І така напівкласична модель, яка зліва зображена, вона, в принципі, інтуїтивна і майже правильна, але в ідеалі, насправді, є принцип невизначеності Шредінгера, котрий, якби, говорить, що ми не можемо побачити просто електрон, що він от на такій орбіталі навколо атома. Це все-таки буде якась ймовірність знайти його там. Ми не можемо одночасно бачити його, знати точно його імпульс і точно його положення, тому в реальності це от такі хмарки і орбіталі, які хтось, можливо, зі школи пам'ятає, хтось цим займається, і взагалі чудово це знає. Тобто періодична таблиця елементів. Чим далі ви йдете, тим більше ви, по суті, цих електронів закидаєте. І ці на орбіталі. І ці орбіталі поступово виростають, виростають, виростають. І от тут зображено, як там може буде 3s орбіталь, 3p орбіталь. Я не буду тут детально на цьому заглиблюватись, але просто, щоб інтуїтивне якесь розуміння мати. Ну так, ще важливий момент, мабуть, треба сказати, що електрони це ферміони. На них розповсюджується статистика Фермі-Дірака, тобто вони не можуть, за принципом Паулі, не може бути два електрона в одному і тому ж стані знаходитись. Звідси і виходить така картинка, тобто у електронів є спін, така характеристика квантового як спін. Неважливо, що це, по суті, стрілочка вгору або стрілочка вниз. І поступово ці стани, тобто кожен наступний атом, у нього все більше і більше електронів навколо атома, і по суті, ну, це і створює от різні хімічні елементи. Тобто, коли ви дивитесь на таблицю, на періодичну таблицю елементів, ви по суті бачите наскільки різні характеристики просто через те, що додався електрон. І це також таке хороше інтуїтивне пояснення, чому інертні гази, котрі там останні в останньому стовпчику, я тут не включив це в картинку, але в них просто якраз буде, ну, тут, наприклад, у залізу, яке в нього замощення всіх рівнів. А коли ви подивитесь на інертний газ на неон, наприклад, то в нього просто тут буде всі ці рівні будуть заповнені, і відповідно просто немає електронам, яким взаємодіяти з чимось навколо. Тому якби вони є інертними газами, тому вони так класно не окислюються, нічого з ними не стається, тому що немає чому взаємодіяти. Тепер від кристалічної решітки перейдемо до оберненої решітки. По суті, це, якщо так строго математизовано розглядати, це є фур'є перетворення градки в якомусь сенсі. І так як вузли градки, от ці атоми, вони самі по собі важкі, але навколо них є ці електрони, якими атоми можуть якось обмінюватись, вони можуть якось взаємодіяти. Знову ж таки, ми говоримо не про інертні гази, а про реальні якби, елементи, які є в кристалах. І взаємодія між електронами там проявляється багатьма різними механізмами. То такий перехід до оберненої структури він дозволяє нам подивитись на фактично стани електронів. Тобто від того, що ми бачимо просто кристал як ну, в прямому просторі, як набір атомів за такими-то координатами, ми переходимо, по суті, до простору імпульс-енергія, і як легко здогадатись, ну і побачити по цій картинці, у вас чим більша буде відстань між атомами в кристалі, тим менший буде імпульс між такими от елементами елементарними у оберненому просторі. І важливий ще нюанс, що так як і кристалічна градка є періодичною, так само і ось ця обернена градка, вона теж є періодичною. Знову ж таки, суто математичний висновок від того, що це перетворення не могло зруйнувати цю періодичність. І на основі, ну, навколо цього є от теорема Блоха, яка говорить про те, що у вас така от одна елементарна комірка, вона може просто домножається. По суті, вона говорить про періодичність такої елементарної комірки. І така елементарна комірка, вона називається зоною Брюлеана. Тут теж все не так просто, як хотілося б. На перший погляд здавалося б, що ну, дійсно от, зробили таке перетворення і все. Але, по-перше, в нас 3 виміри. По-друге, в залежності від того, який у нас кристал, яка симетрія, одразу з'являються такі складні зони Брюлеана, по суті. Тобто для FCC це face-centered cube. Oh, I should have been talking in English, I guess. I'll switch to English from now on. Yeah, you didn't remind me about it, so I mean this will be a recording. Yeah, you should have reminded me about it. So FCC is face-centered cubic lattice. It's this one, and for it the Brilliant zone looks like this. It's just an example. I'm just showing you not the simplest example, but something like more interesting. And for different Brilliant zones, there are some high symmetry points. For example, gamma point is the center of Brilliant zone. K is usually like on this horizontal plane, like the middle of this edge, and so on and so on. And it's actually important because this electronic structure which arises, you need to, like, it's not just like one number, it's a 4-dimensional array, basically, and you need to know like which directions you are studying and what exactly you are checking. So this is the example of such dispersion or electronic dispersion or basically electronic band. Because energy of the electrons, because the momentum of the electron can be written in wave vector k with reduced Planck constant. It's intuitive that the dispersion, so that like the states at which we can see electrons, that they have the shape of parabola, because basically the energy which is vertical axis is the square root, or the square of k wave vector divided by 2m. So it's intuitive that it should be squared, but it's not intuitive why does it have these widths? Why is it not exactly like this dashed parabola like it is? And that's and this is the simple example. That's just one band. It can be more than one, and they can interlap and so on and so on. And this is basically because we have electron-electron interactions, spin-orbit interactions, and many other physical phenomena which arise. Also, important notice that this band is formed by many, like 10 to the power of 20, 10 to the power of 24 electrons, which occupy energy levels by Pauli principle, like they grow higher, higher, and higher, and the maximum level for this spectrum, it's called Fermi level, basically Fermi level or Fermi map or Fermi surface. It's the surface with the level at which electrons have the maximum energy. And just to show you a brief example that it's not always as simple as just one band, that this is, for example, real experimental spectra measured for iron, tellurium, selenium. And here there are 1, 2 bands, and then there is also some gap and something strange is happening. And this is what I've called Fermi surface. So that's like these two cuts are basically when you cut this big picture diagonally and see just this part of the brilliant zone. Remember that I was telling that brilliant zone is 4-dimensional, and 4-dimensional in a meaning that it has kx, ky, kz. So these 3 momentum vectors plus energy. And it's hard to obviously show like 4-dimensional object in 3D. So people, we need to like improvise and do some like special presentation of it, like special cuts. So this is basically the cut of the brilliant zone at some kz, and then we do another cut through it at specific direction. A bit more about band structure. So all these bands that I've just shown you obtained experimentally, they form like the amount of them basically shape the bands which can cross the Fermi level, this maximum level at which electrons are, or can be lower, or can be much higher, or there can be some big gap. And why this is actually a good example of why electronic structure is important, because when you look at it, it perfectly describes you why different materials act differently. For example, in metal, these electronic bands, they don't stop at Fermi level. So like there are states which can go higher without any big gap, without gap at all. And that basically means that it's easy for electrons to jump between different atoms, to jump between each other. And this is basically an example of copper or iron, any conductor. For semi-metals, it's a bit more difficult. It's a bit more tricky. It's like there are some states, but only some, and like that makes appear some other different interesting features and properties. But the most famous example of this are probably semiconductors, like all your phones, all your computers, the chips, the CPUs, the GPUs, like transistors are based on this, that you make a small gap. And this small gap can be actually, it's like hijacking the physics, hijacking the crystal to make a simple logic that if you apply slightly less, then it's in one state. If you apply slightly more, then it's in different state. And it's fine-tuned exactly by this small gap and energy Fermi level being at some particular distance from one level or another. And yeah, p doping type and n doping type and so on. And insulators also intuitive, I think. Is it intuitive actually? Why do you think on this right part? Why is it insulator? If yes, and this gap is actually quite big. Like here, there are no numbers, but in electron volts, it can be several electron volts. And electron volt is, yeah, it's not like maybe you are more used to joules or to other units of energy, but basically one electron volt is 10,000, like equivalent to the temperature of 10,000 Kelvin or something, around 10,000, 11,000 something. I can't remember from my head. So like huge gap, and yeah, electrons just can't jump over that at room temperature at least, unless you are at 10,000 Kelvin. Then yeah, then it's not an insulator. But otherwise, yes. Capital E is energy. So yeah, vertical axis is energy, and horizontal is just the number of states. So like we reduce that k vector, we just summarize all the states that there are at any energy level. And now turning to machine learning, the applications for physics and condensed matter physics in particular, they started to arise like single cases even before these dates that I'm showing here, but in majority, like big events started happening, I would say around 2020. APS, for example, it's a big physics conference happening at USA. And in 2020, it had several different sessions. One of them was like machine learning for quantum matter. So it's already was getting big back then. So it's nice that it caught up because, like you probably also know, in cosmology and in high energy physics, it started earlier, like around 2015, I think. And another example, like we did data science school just this spring in CAU, and one of the speakers that will be here, I believe the day after tomorrow, Nitesh. We also invited him, but online. It will be great to meet him live. This school was quite a success. It was also interdisciplinary like this, and it's nice that also a lot of people here are from from last year's school here at UKU. So it's nice that it's such a fast developing and active field. Now back to physics a bit. Those band structures that I was showing to you, they can be calculated, spoiler. And DFT, you might have been wondered how it's, what's the abbreviation for it? No, it's not discrete Fourier transform, it's density functional theory. And basically the idea of why at all we need DFT. Okay, I'll explain first about it, then we'll tell more about that. Basically, to calculate the electronic structure, you need to solve Schrödinger equation. And you might know that Schrödinger equation is not an easy way to solve, like it's solved for hydrogen, but for more difficult structures, molecules, crystals, it grows in complexity quite fast. It can't be solved. And DFT is like a workaround to solve it without solving. So we assume that all properties can be determined by electronic density, which is actually like not an assumption, it's a fact. but the big assumption is that we can, through Kohn-Sham equation, we can, instead of looking at all the electrons, at all the states, we just look at their density. And their density, through a lot of workarounds, we can like connect it with the actual electronic states. And there are a lot of software already existing for that, to do that. Some notable examples are FPLO. It's developed at IFW Dresden. WASP, by the way, FPLO and WASP, they are both not free. You need to pay for them. And I think WASP license costs like $3,000 or $4,000. So these are big software packages, like big industry uses it, R&D uses it. Like it's must have for like not the only program obviously which you need, but it's must have for material study. And Quantum Espresso is the open source one. Like it actually even does some things better than WASP, for example, but in general, the capabilities are more or less the same. Some things are done better there, some things are done better there. It depends. And to show you how explosive and big DFT got, Walter Kohn-Sham equation I showed above got Nobel Prize in chemistry in 1998. And John Purdue, he is the author of PBE potential. It's widely used, very good approximation of many systems and very good starting point. It has by now like 200,000, maybe now already 200,000. I don't know. I made this screenshot a week ago. And he is one of the most cited physicists as far as I know. So it really grew big. So now applications, I've mentioned them already a bit, but it can be, it is important for drug delivery when you need to, for example, synthesize some material for which your vaccine will connect, and then it will be from that in your body under different conditions, it will transfer to the cells or something like that. Structural materials, obviously, how to make materials which are stronger, how to make materials which are stronger and lighter. Of course, also more chemical sides of things like catalysis, surface sciences, magnetic properties as well, geophysics, and I think like basically anything you can think of that involves materials. And another important aspect regarding difficulty, like yes, it makes it at least possible to calculate the properties of the material that you can calculate it at all, not just Schrodinger equation, you are done, you just can't solve it for atom more difficult than hydrogen. But still there are limitations. For example, this is what doping means. Doping is basically taking your crystal, taking one atom out and putting something else inside. So on the right, there are two examples, p-type and n-type semiconductors, which I've mentioned before. And it's just, you had silicium, and then one of the nodes, you removed silicium and put boron, or if it's n-type, it's the opposite. You put, instead of silicium, antimony. And what's the fundamental difference? The fundamental difference is the number of electrons again. So you had everything balanced, everything was like, everywhere silicium had just 4 electrons, everything is cool. Then suddenly there is one node in which the number of electrons is different, and it changes electronic structure, obviously, because there is some disbalance. When it's something that's symmetrical, and you know that, for example, you had iron selenium, and then you made it, instead of selenium, sometimes it's selenium, sometimes it's tellurium. When it's 1-to-1, it's simple. You just increase one elementary cell by 2, and it doesn't grow that fast. But if you want iron selenium and 1/100th of tellurium, then your unit cell grows like, I guess, exponentially, like to the power of 3. Because you need to make one elementary cell which would include this structure, which you can after that repeat. you need to make it like 100 times bigger to encompass this one atom that you added. And for DFT, difficulty rises with it also rises exponentially. Like it's fine to calculate something that has 3 atoms per unit cell. It's fine 20 atoms per unit cell. Like, yeah, you will calculate on some supercomputer or cluster, but it's doable. But when it's 100, 200, 1000, then no. Then at some point it just stops being reasonable. And actually one of the directions where machine learning is used in this field is approximation of DFT calculations in a way that you did calculations on structures where it's, for example, iron selenium. Then you did also for iron tellurium, for iron selenium tellurium, and then you just ask your neural network, which trained on this, to guess what will be when it's just 1% of tellurium, for example. I mentioned it briefly because I won't be covering it in detail today. There are too many different applications, and that's not the one I'm working with. A bit about what has been done by our group. This is, for example, a recent publication from Physical Review Materials, where the group from CAO and IFW Dresden, it's collaborative work. They actually predicted this material, titanium, selenium S, and then also managed to grow it. So like it's a nice complex study. Another example is the platinum bismuth 2. This material is actually very interesting. I don't know if I have that. I'll say a few words. This material is very interesting because it at the moment, it seems like it can carry Majorana fermions, and these, I won't go into details, just no time for that. But these particles, these special states, they can be used for creating of qubits in quantum computers. And if you use such structures in quantum computers, then they are much more resilient than current ones, which need extreme cooling and high vacuum. In this case, it can be coherent. Several qubits can be in coherent states. If you do something like that with this material, they can be coherent at very low temperatures, but it will be kelvins, not millikelvins, and that's already like fundamental jump. Other interesting example of what our PhD student does, Oleg Feya is, he works with me in the machine learning lab. He specializes on DFT, and a lot of examples I will show after. All of the examples that involve DFT involve him as well. Maybe you have heard recently sensational news that there is room temperature superconductor, LK99. It was widely talked. The Korean group reported that they've grown it and that they see that it's superconducting. Then quickly after, I think it was in May this year, around that time, quickly after that like other groups started measuring, and they shown that no, like doesn't look that 100%, and it's like still been researched, but it looks like it's just it has some properties, but it's not a superconductor. It's not as good as as everyone would want it to be. And the interesting characteristic of it is that again, this electronic structure that I was talking about, it's very complex, like you see. And while we are here, again, just to remind you and maybe to give you better understanding, like all these mesh below, like lots of weird lines, which is hard to read and understand, and they are all over each other. These are all those electron levels, like that when I was showing the periodic table, those are all those core electrons which are lower, and we are not very interested in them. Like, of course, they influence a lot of stuff, but the most interesting things are the ones which are at the top, the ones which are at this 0 Fermi level. And this is the zoomed in picture. And interesting thing for this material, actually, when we started the PhD student from CAO, when he started from Institute of Metal Physics, actually, but he collaborates with us. When he started calculating it, and also calculations from other people, they show that there are flat bands near the Fermi level, and just empirically, like I said, there is no theory for high temperature conductivity, but empirically, usually when you see such bands which are pretty flat near the Fermi level, that's a good sign that there is superconductivity or some interesting properties. The PhD student did his own calculations. Also, he also showed that he even did the spin polarized one, which is like more complicated, more complex thing, and this was very nicely computed by him. But yeah, it looks like it's still just it's not the superconductor. It looks like it's just the antiferromagnetic. Another work of our current PhD student, just first year, the ITO collaborated with Oleg Feya. ITO films, they are used in some variation of them is used in your phone. So it's like the material which the interesting material which is transparent and conductive, so which allows your sensor controls to work. And the idea of this project is to create ITO film which is also superconducting, and of course it also involves a lot of DFT calculations. But this problem arises that the unit cell can be too big, and the question is how to calculate it well enough. Yeah, the last purely physical example is doped graphene. This is one master student and one PhD student from KAU. This is also a nice example of collaborative work where one part is growing samples and another part is one part is doing experiment, actually, not growing, just doing experiment. Another part is calculating it. And here the idea is like you take two sheets of graphene, you put some atoms between them, like cesium or rubidium, I think in their case, and you try to improve the energy function of them. But basically, long story short, the idea is to make the thermoelectric material which can be used in energy sector. And now more of machine learning. Master student of KAU Bogdan Semenyuk, he did an interesting work using genetic algorithms. It's very nice that speaker before me mentioned them and described in details. I won't need to stop much on that. So the idea is to predict some new crystal structures of unknown materials. And obviously, just doing DFT for them is not a normal option, because like to calculate something, especially if the structure is difficult, it's very time consuming. So the idea here is to create some random, like you have initial population of random crystal structures with some elements that you want. And that article of titanium selenium S, which I've shown earlier, it was also made in a similar way. You create the initial population, you apply different mutations to them. In this case, unlike previous speaker where it's just semantic writing, just functions, mathematical functions, here instead of functions, you have crystal structures, and the building blocks of them are atoms which you write down to be used as, for example, iron, selenium, tellurium, and then or silicium and oxygen. And you start making mutations with them, rotation, mirroring, just removing some atoms from the crystal structure, varying the size of crystal structure, and so on and so on. And on each, and you do it for many generations, and in each generation, you relax this structure. Relaxing means like recalculating its properties, how physical it is, not just randomly throwing balls into the basket. And because if you do that with quantum espresso, it again defeats your purpose. There is extra step here, gulp. It's like very simple, very cheap and expensive, very cheap computationally method, which is based on electrostatic, basically Coulomb calculations, which are easy to do. And quantum espresso is being used only at the last stage. And thanks to that, we get a huge boost in speed, which makes it basically possible. And another interesting aspect that you need actually to compare, like to know if your structures are the same or not, because like when you just see that this is one crystal, this is another crystal, and these are one coordinates, these are another coordinates, okay, you can compare by your eyes, I guess. But when there are like many generations, many childs of previous generations, which looks optimal, you need some metric to compare them. And one, like the metric that was created, I won't go into details here because this paper actually covers that topic pretty well. Basically, it's based on checking the nearest neighbors of the atom and how many are there in specific graph, and then you create basically such profile of it, such fingerprint, which you compare structures to each other. And here, the distance between silicium and oxygen, you compare it to the one from predicted state and from the material for which you calculated it, and you see that it aligns well. You can calculate the difference, so it's a nice metric. And here you can see the result of the work of such algorithm. I was showing it before. I didn't say a lot about it, but yeah, basically what we are minimizing the energy of these structures, the energy per atom. Basically, it's the same. So the energy per atom, and this creates a big hyperparameter surface on which you do these new generations, mutations, new generations, and so on. And on the right, you can see examples like first generation, just random set of crystals, crystal structures, and this dashed line is just the average. Obviously, like it's not an approximation, doesn't make any sense. It's just to show the general dynamics that different. So it's just random. It doesn't make any sense. But already on 10th generation, a lot of structures. Each circle is a structure. Different colors correspond to children, parents, mutated children, and so on. Because yes, some children from previous populations, they can proceed to the next generation if they are good enough. So it's not like each generation is completely new. Some instances get transferred. And you can already see that here a lot of them are low at this energy. And at the 40th generation, it's already even better. Of course, on this picture, it's not clearly seen, but then when we select from there the best structures, we end up with the fact that actually this approach, where we just said that we have silicium, we have oxygen, predict all the crystal structures that will be stable, that actually can exist in real life. And the result is pretty good. It predicts all the different phases of silicium or O2, basically. So it has stickovite, coacite, alpha quartz. So the things which material scientists know, this phase diagram which they know, all of them are being predicted. It doesn't give you the exact temperature, the exact conditions at which it will be like created, but it gives you, like, predicts that this material actually exists. The only one which wasn't found is coacite, but it is most likely due to the fact that if we included more generations, not just 40 but more, and if we also calculated it a bit more robustly, then it would arise most likely, because like it just got lost over the others, but it's not a fundamental flaw. And on the left, you can see predictions from this methodic, which is called cleverly H ISE, gulp, and quantum espresso. Basically, ISE is the library on Python. You can check it on GitHub. It's atomic simulation environment. It has a lot of other cool things. If you want to do something with material science, you can play with it. It has a lot of features for this. And next plan after this, because like I mentioned, there is gulp for these cheap calculations. This is the current stage. Like this direction stopped for now. Like the student goes to PhD and will continue this work. But next stage, because of that fact that I've mentioned, we are using gulp. Gulp also doesn't come like completely free. You need to know some potentials for gulp as well. And for quantum espresso, actually true for DFT. If you want to calculate something more complex, sometimes you need to develop to make a precise calculation, you need better interatomic potential, and this is where machine learning helps. These papers are both from Alexander Isaev. He is a computer chemist and material scientist, and his main work is actually devoted to machine learning interatomic potentials development. They developed ANI. Do I have it? No. They developed this ANI1 potential, and I think they made a lot of variations of it, but these are mostly for chemistry and for molecules. So they trained it, they trained it and developed it. It requires tremendous amounts of data, but they trained it only on up to date, I think, 11 different elements. And these elements are mostly those which are common in organic chemistry because of drug industry, medicine, and so on. So it's not very helpful and suitable to us yet, but developing something like that for other elements would be very cool. The idea is based, like one of the core things which they use is as a descriptor, they use atomic environment vectors, which include information about like atomic environment of the of your node, and also about orbital environment, so like information about electrons. And then they put that into the neural network. Recently they also, I think, turned it to graph neural network. So I won't stop in details on this, just the results that it really needs huge amounts of data, because like you see on the graph on the left, the performance of this any potential, which can be measured, like how good it is, it can be measured, but by how much is the error in energy, basically. Like you've calculated it with DFT, and like accurately, and as accurately as you can, like without cutting any corners. And then you use this machine learning potential, and you can see that for all of this, like when you go by one order more, you decrease this error by much, like by 1.5 basically. And even more visible here, where the more the bigger the training size, the training set size, the more heavy atoms you include. At that point, it was 8. Okay, I don't remember exactly. I think it was trained on 6, but predicted even for 8 atoms, heavy atoms in the molecule, like some mixture of them. And that's also a cool example that it was working well for something that network was not studied on. And you can see that the error like drops very heavily with the size of the training set. And very recent example regarding materials discovery, GNOME, the pipeline which DeepMind developed, it it partly does what I've mentioned before with genetic algorithms, but it's a completely different approach. It is based on graph neural networks, and there are several pipelines included in it. One through structure, another through composition, and then on top of that, they calculate DFT. And the impressive result is that they actually predicted 2 million stable materials. Good luck checking all of those, like experimentally. And even when you sort out all the like, even if you add extra criteria and sort out those in which you doubt, like some meta-stable ones, it's still 389,000 crystal structures, new materials, and that's a huge jump, because up to that point, until this was developed, the famous platform, famous site for these types of things, Materials Project. On Materials Project, you had, I don't remember exact number, like 50,000 structures, approximately like that. Materials Project is just the database and the toolbox, which can be, there is API for it. You can access it through the web as well, just as on the site, and it includes all the basic information about materials, their calculated electronic structure, and so on and so on and so on. And there were like 50,000 known structures, which are some metastable, some stable, which exist. And here suddenly, like, you find out that there are several times more, and humanity never knew about them. Maybe there is like some much better semiconductor with which your computer will be 10 times faster, and so on and so on. So like the amount and the meaning of this discovery is very huge. And actually people didn't stop about that. I found out just before this school. This is the leaderboard for all such models. They all use lots of data. And GNOME was the leader. But just recently, the preprint on arXiv is from, I didn't put it, well, it's from May. I think from end of May this year. It wasn't published yet. I think they are going through the review. But they achieved even higher precision, accuracy, R², all the metrics are better than GNOME, and it's open source, if I remember correctly. I might be mistaken. Okay, I don't remember. I need to check. But the cool fact is that they did not only predict a lot, but they actually, it's also a graph neural network, and with help of it, they can even make phase diagrams. They don't just predict material and its properties. They actually add a whole bunch of properties around that. And in theory, this can be like a tool which tells you that this is material X. To do it, you need such temperature, such pressure, such conditions in this order, and you synthesize that material. This is very cool. If it comes through review, very impressive result. I didn't have time to study it in details yet, because it's, again, very recent. And probably last thing for today, another approach, not based on DFT, just the prediction of critical temperature of superconductors. Like I said, superconductivity, especially high temperature superconductivity, it's still an unsolved problem, and you can't calculate it. You can calculate it, but you can't predict it easily. And from electronic structure, it's not straightforward to get the TC. of the material that you just calculated theoretically. And one of the approaches that these authors used, they took a lot of materials from crystallographic databases, ICSD, which is the biggest database up to date of all the crystal structures. And this database, what it includes? It includes crystal parameters, ABC, the angles between them, like the symmetry, the number of valence electrons, the number, like the number of orbitals, like mostly not technical, but mostly descriptive parameters of the crystal structure. And up to add to that, they used a supercon database, which is purely for superconductors, and it has
use how you can use graph neural network there.
You mean the input for this?
Yeah.
The input for this is basically atoms, like which atoms you put into the equation. Like, for example, in this case, in this simple case, silicium and oxygen, right?
Mm-hmm.
And you don't say that it's silicium O2 specifically. You just say silicium, oxygen, and then you make some random structures, like just coordinates of these atoms.
Mm-hmm.
Like you have the unit cell, where this is coordinate of silicium, this is coordinate of oxygen, this is coordinate of another oxygen, this is coordinate of another oxygen, and then like you make the translation symmetry for this, like you repeat it, you create crystal out of it. And there are a lot of such structures. And then you start relaxing these structures, like make them come down to the most optimal energetically, and some are obviously very high energy, so they are like they are not realistic. They won't exist in real life because it's just not optimal at all. Some come to some minimum, and then through these iterations of mutations, like you've changed something, you tried to increase one of the edges, and so on, or you just threw away one of the atoms with in each generation. You do that, then you relax, you calculate, you see this energy, you again drop part of them, and so on and so on.
And what is the output? It's structure.
The output is also structure, yes.
Mm-hmm.
And this is also what fingerprint is used for. Like you calculate, you take the node and you calculate distance from it to neighbor atoms. And for different crystal structures, if you do it cleverly, you will have it unique, more or less. Like not absolutely unique, obviously, but unique enough to distinguish different phases, different examples.
Mm-hmm. Okay.
And you also asked about graph neural networks.
Yeah. If you have any ideas.
We didn't think about it. I don't see how to add DFT to that, except for very last stage when, well, like actually GNOME also did. Like they predict something, and only then they give it to the DFT. It is possible, I guess, but I would expect that you need huge resources for that. For maybe for some simple structure, it will work without needing supercomputer being loaded to a big capacity of it, like with lots of GPUs. But for anything more complex, I believe even in this leaderboard, you see that GNOME, for example, it had a training set of 6 million structures, and actually 89, I don't remember, 89 is proprietary and 6 is like open, you can download them. I don't remember what they meant by that, but it's the task which is like on a large scale, large higher scale, like big corporations can do that. But for university, like, yeah, if it's some collaboration of many universities, then probably you can do that. And this machine learning potential that I was talking about, that they made it up to that date, I think for 8 heavy atoms, and now it's 11, I think, 11 heavy atoms and all sorts of combinations for them to predict molecules, to calculate molecules. For that, they didn't use just one cluster. It's the collaboration of several different universities in USA with lots of teams working on it. So it's quite a huge task. In comparison to this being done by mostly Oleg, a supervisor, and his student Bogdan. So this is, and also it's more interpretable. Like it was mentioned by previous speaker regarding the approach. Like, yeah, when it's neural network, it will be hard to understand what was inside. But yeah, graph neural networks is a good attitude to this, because I didn't mention it. Graph neural networks win from representation of these crystals in form of graphs.
Yeah. Okay. Thank you.
With this method, with this, no, unfortunately, no, because these mutations, they have physical sense in a way, like, yeah, you took the crystal and you strained it, or you took the crystal and you just cut it, took all the atoms from some nodes of it, yeah, but it doesn't directly explain you what's the temperature or what's the pressure. It's just like some manipulations with atoms, and then you also relax it. So unfortunately, this method at current stage, it doesn't provide that. Unlike these graph-based methods with graph neural networks, this paper, they didn't focus on it, but in this recent one, MatterSim, they actually show examples where they calculated the material and they have detailed phase diagram of them. But actually, there is one huge asterisk up to all of this. I thought I will tell about that tomorrow, but I can mention it now, that all this, it's very good, it's very important, it's very helpful, but DFT is not, DFT in particular, and these methods, as a result, because they are partly based on DFT, it doesn't give you the ground truth. It doesn't give you the absolutely correct result. What they give you is the general understanding. For some materials it's better, for some materials it's worse, but generally you know that you calculated it for iron selenium structures. In experiment it's one value, in calculation it's twice the value, and people just know that already empirically. So it's not the theory of everything. It's not the theory of high temperature superconductivity. Like I said, it's ab initio. Yes, it's from first principles. It kind of solves the Schrödinger equation, but it's still an approximation. And even with these graph neural networks, which are based on which incorporate DFT at some stage, it won't give you like absolute 100% phase diagram that you need 500 Celsius at 1 gigapascal to grow this sample. Like maybe it will be that, maybe it will be twice less, and you need to find those correlations yourself. What's important that it gives you the dynamics, it shows you general region to look at, and that you can compare different points, although it can also be sometimes tricky. With experimental data, it's complicated. I'll explain tomorrow because in experiment you don't get where was it? For example, this, yeah. In experiment you don't get this big picture. You get just tiny pieces of it. For example, I don't know. For example, let's take yeah, I didn't explain. Maybe I should have taken more time because I still have 15 minutes. I might explain now. This on the right, smaller picture, which is zoomed in this area. Actually, this as well, they're both the same. They go in these specific directions, like I've mentioned to you. When you have the brilliant zone, you go from like center of brilliant zone, gamma, then you go to R is I think up middle point, then from M, yeah, M is like edge point, then from there you go to K. So it's like specific directions in brilliant zone, because again, 3-dimensional plus energy, actually 4-dimensional, it's hard to represent it, and you need to like make some representation of it. And when you look at it, you don't measure it exactly in one piece from the experiment. In the experiment, what you measure is you fixate it at gamma point, for example. You measured cut like this. For example, cut like this. I don't remember if it was gamma point, but let's assume that it's gamma point. And this is just one cut in specific direction, like diagonal. If we take, again, the same gamma point and take horizontal cut, it will look different. If we take vertical cut, it will also look different, obviously. And this is just one cut. And to map it like here in calculations, you actually need to make a set of experiments and then combine them. And that's like, I don't know, one night at the synchrotron. Like you came there, you cleaved the crystal, it didn't cleave well, you cleaved another one, it also didn't cleave well. Then it's already like past 3 a.m., you cleaved another one, it works, and then you measure until morning, and you got like 500 megabytes of data, you like started fitting it, started like gluing it together, fitting it, and so on and so on. And then you, after data processing, you got such thing, because what you get from the experiment is such pictures. Yes, it's cool, actually. It's very cool that it's basically the photography of electronic structure. Like you see with your eyes where the electrons are, basically. And in reciprocal space, of course, but still, you see where they are by energy and momentum. Like it gives you a good understanding. But you still need like to process them, like to glue them, to fit these bands, to know that this is actually like the top of it, that this is actually the gap, and why this gap arises, that, oh, it turns out that it's superconductivity. So when superconductivity, there is gap here opening. So it, short answer, you can't just get from one experiment all this. You get small pieces and it takes time. So to compare it to experiment is difficult. To compare it to different models, that's done here. I think GDB10, it's some different, some other, I don't remember, some other machine learning potential, but yeah, this was previous one and this is just new one. So comparison like that. Or for example, PM6 also. Yes? Not quite. It's a bit more complicated than that. Just instead of solving the wave function, instead of solving the psi, you through a set of procedures, you operate with density of states. Yeah, and it's actually density functional, so it's like function of function of function. And what you solve, basically, you solve in the end Kohn-Sham equation. And it's actually proven mathematically very well that, yeah, it's identical, that you can do that. And it was very cool when people created that, because before that, it was like you couldn't calculate even those things that can be calculated like now. Yeah, like, yeah, they're expensive, but at least now you have the method. Before, yeah, you had some approximations, but people were looking, how can you like hack this? How can you, instead of like solving this tremendous mathematical thing which arises from Schrödinger equation, how you can come to some other basis at which you can get reasonable results? And turned out that it was through density. Okay, if there are no more questions, I'll finish with this description of prediction of TC. It's quite short, actually, but I like this result a lot. It's from 2018, and unfortunately, the crystal structures, up to my knowledge, maybe there is some new paper and I've missed it, but up to my knowledge, most of the materials which they predicted, they turned out they didn't show any TC, they didn't show any superconductivity, but maybe some will, and this is not the most impressive result for it. So yeah, let's again return to what was the idea. The idea was to use these databases of crystal structures, of their properties, and then add into that database SuperCon, which has TC and some extra features, and also combining it with A-Flow. A-Flow is another database which and an instrument as well, which includes some calculations as well, some electronic structure from DFT. And by combining all of those and splitting materials superconductors, splitting them into groups like superconductors which have TC less than 10 Kelvin, superconductors which have TC more than 10 Kelvin. Cuprates. The cuprates are the superconductors which have a copper oxygen layer. It's just a separate class. It was one of the first ones which were found in 1986. Like, yeah, I didn't mention it. Superconductivity up until 1986, it was thought that, yeah, it's more or less understood. Like there is Bekasha theory, Barton, Cooper, Schiffer. Like the theory says that 27 Kelvin is the maximum temperature at which superconductor can exist, and that's it. And then in 1986, just by accident, there were no machine learning. There were no, well, there was machine learning, but no, like today, there were no GNOME and other methodics which could predict two tons of materials. It was just discovered by accident that ceramic, the thing which is expected to be actually an isolator, that suddenly it's superconductor. And it's not only superconductor, but it has TC, which is higher than those 27 Kelvin. And from there, it started like this field of high temperature superconductor, which is still not high temperature. It's still like cryo temperatures, but at least some of these superconductors can be obtained with for example, liquid nitrogen temperatures. So cuprates is one of the big classes of that, and iron-based superconductors is also more recent class, which I've talked about before. And they made random forest for classification to distinguish which materials are which have more TC, which have less TC, there were a lot of features which were used in this ensemble of decision trees. And the result is quite impressive in a way that it gives you understanding of what is like, adds some intuition to what is actually happening, because when they did it, they saw that different materials like cuprates, for example, when compared to low TC materials, they act differently. And model, when you add on top of this random forest, when they performed also regression, it predicts TC pretty well. But they took on the class of low TC, and then they see that it doesn't predict well the cuprates, for example. Or they do it for cuprates, but don't predict well low TC. Or they take it for iron-based, but it's bad for cuprates, and so on and so on. And what's cool about it that you can see which decisions played bigger role in one case or another case. And potentially that can, for example, I didn't add that table here, but I think for iron-based superconductors, for example, it was something with melting temperature or something, some counterintuitive parameter like it. It was not at the top, but for iron-based superconductors, somehow it was among the top features, which was influencing the TC prediction. And for cuprates, it was not playing the role. So like through investigation of these parameters, you can get extra intuition of what is important for superconductivity. Like I was talking about those flat bands, like, yeah, you have flat bands, maybe it might be a superconductor, like it's a good sign. Like if you have material with that, you need to explore it more. And so on, like this method provides you extra criteria, which can be good for that. And besides that, just as a big result in one number, like they achieved R squared almost 90%, which is like huge precision, very good result for all classes of materials. This graph, yeah, here they combined cuprates, iron-based, and low TC, all the structures that they have. And also important notice is that maybe it would perform better, and maybe there are actually better approaches than random forest, because like, random forest is very cool, but like maybe you also can do something with graph neural networks here. But there are not that many data for it. Like yes, you have these databases, but SuperCon doesn't have tens of thousands superconductors with TC. Their number is just limited, just because like there are many superconductors, but not that many. And to get better understanding, you just need more data. It's just not known to humanity yet. So to me, it looks like it's not some method limitation. But maybe, but more the limitation of the data, that it's just not enough to make this data-driven discovery. So you still need either more data or better understanding from physics. With that, I think I will stop, and maybe you have more questions. Thank you. Okay, then thank you. I don't know if Alexei is here. Did Alexei already come?